Are there any questions on anything? Any questions? Is there anybody out there? Can you guys hear me? Can someone hear me?
We're here.
Okay. All right. Thank you. Are there any questions? I guess not. Okay, so last time or yesterday, if you watched the video, I started talking about projectile motion. Projectile motion is this idea that you have an object and you give it some initial velocity. It makes this nice parabolic trajectory. Once it leaves your hand, it's under the influence of gravity only. There is an acceleration in this direction. That's the y direction. There is no acceleration in the x direction. So it's a constant, steady motion in the x direction, and it's free fall motion in the y direction. So for the x direction, well, let me say this. Typically, you're going to break v initial up into vx initial, which is v initial if this angle is theta. You're going to break it up into vx initial, which is v initial cosine theta, and vy initial, which is equal to v initial sine theta. That's not always true. Depending on how theta is defined, you could have these being interchanged, something like that. You have to pay attention to the way theta is defined, what the angle, where the angle is being measured from. But this is this is the most common case, okay? So you have some equations of motion in the x direction. It's pretty darn simple. For Vx initial equals Vx final. Whatever that initial velocity was in the x direction, that's the final velocity. We're ignoring air resistance. So this is true. Also, you have the equation x final is equal to x initial plus Vx initial t. So this would be the time of flight, the time that the projectile is in motion, and this is a starting position. So that's all that's really going on in the x direction. The velocity does not change. In the y direction, however, there is an acceleration due to gravity. So you have that familiar equation, y final is equal to y initial plus vy initial t minus g over 2 t squared. Also, vy final is equal to vy initial minus gt. That's that velocity acceleration equation. If you know the initial velocity, the acceleration is g, and the time, you can figure out the final velocity in the y direction. Occasionally, you may be able to use that other equation, vy final squared minus vy initial squared is equal to minus 2g y final minus y initial. That one in projectile motion, I don't think gets used a whole lot, but it's there, okay? And the idea of these problems is you're going to know something about the x direction, the initial velocity. You typically have to solve for something in one direction and then use that solution to find the solution for the other direction. When I say direction, I mean x and y. Okay? So this is 2D motion. You have a nice parabolic trajectory. Actually, it's not a parabola, but it's close. Anyway, this is the idea. So I did an example yesterday. I want to do what I'd like to do is go through some of these homework problems from chapter 4 and use those because that's what you've actually got to do and get a grade on and all that. So I'd like to go through some of these homework problems. So if you're able to open up WebAssign and go to chapter 4. Nobody has any questions about the problems in chapter 3? Okay. I want to start with this sort of classic problem, which is number 3. Okay. This is chapter 4 for us, number 3. And if you're reading along, it says, in a local bar, a customer slides an empty beer mug down the counter for a refill. The height of the counter is this is my numbers, is 1.34 meters. The mug slides off the counter and strikes the floor 1.2 meters from the base of the counter. With what velocity did the mug leave the counter? What was the direction of the mug's velocity just before it hit the floor? So this is very similar to the example that I did yesterday, only it's actually a little bit simpler. Okay, so here, let me get a different marker. These markers are dying. Let's see.
What number was it?
Number 4 from chapter 4. I'm sorry, number 3. Number 3. Number 3, chapter 4. Starts out in a local bar. Okay. And this one's okay. So here's the setup. I'll just use variables at first. So here's the edge of the table, or here's the table, or the bar. Here's the object sliding. It leaves the edge with some V initial. Okay. Once it leaves the edge, it's a projectile and it follows that parabolic trajectory. It hits here. Okay? So in the problem, they give you the height of the table, which we'll call H. Keep saying table, I guess it's a bar, but okay. You know this height H, and you know this distance, I'm going to call it just X. No, I'll call it D. Okay. And the question is, what is the initial velocity of the beer mug? Okay. Here's what's happening with this. The only velocity that you have is in the X direction. It slides off this way. There is no initial velocity in the Y direction. So Vy initial is equal to 0. Vx initial is just equal to V initial. Okay? V initial. Let's see if we can figure out what we know in the X direction. In the x direction, you have x final minus, I'm going to write it like this, x initial is Vx initial t. This is what I'm calling d. That's that distance. Make this x initial, make this x final, then that distance d is x final minus x initial. Okay? Problem. We don't know t. We don't know the time that it was a projectile. However, we know the height of the table, so we can use the information that we have in the y direction because there's no initial y velocity. So in the y direction, you have y final minus y initial is equal to Vy initial t minus g over 2, okay, t squared. This is h. Well, okay. This is negative h, right? Y final is 0. Y initial is h. So this is minus h. Okay? This is 0. Because Vy initial, it came off the edge of the bar just with an x velocity, no y velocity. So you end up with negative h is equal to g over 2, or negative g over 2 t squared. Okay. Well, this becomes, these cancel out, and you get 2h over g underneath the radical is equal to t. And we know that. We know h, we know g, solve for t. Once you solve for t, you can use t over here to find d. I'm sorry, you can use, we're finding Vx initial. We know d, we found t over here, we can find Vx initial. You follow that logic? I hope. What I had to do is solve in the y direction. Then once I found t for the y direction, I could solve for the x direction. I could solve Vx initial. Okay. Let's look at part B. In part B, it asks, what is the final velocity? Remember, we just found in part A, we found Vx initial, and that equals Vx final. That does not change. When it hits the floor, the component of its x velocity is exactly the same as it started, okay? But the y direction, it's gained some velocity in the negative direction. So when it hits the floor, it's like this, okay? There's V final, right at the point of impact. All right. We know Vx final, finding Vy final. Oh, let me say that we also found T in part A. We did that first. We found T. From finding T, we were able to calculate Vx initial, which is equal to Vx final. So in part B, they're asking for that final velocity. So you can use Vy final is equal to Vy initial plus, minus GT. Well, Vy initial was equal to 0. So you get Vy final is equal to negative GT. Use that T from part A. Vy final better be negative because the object's falling. Okay, if you had a projectile that was traveling like this, and it's rising, 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 okay, that's different. You have a positive y velocity, then a negative y velocity. Knowing Vy final from the information in part A, do what we always do. V final magnitude is equal to Vy final squared plus Vy initial squared. Okay. Oh, I'm really messing up. Vy final squared plus Vx final squared. Sorry. Okay. What about the angle? Well, I'm going to draw a little bigger picture. Here's V final. Vx final. Vy final. So finding this angle theta, I would just take, for theta, that's going to be equal to the inverse tangent, or arctangent of Vy final divided by Vy initial. Jeez, that is wrong. Jeez. Vy final divided by Vx final. Come on, brain. Okay. Any questions on that? This is going to give you a negative theta. That's fine. If you want to make it positive and say below the horizontal or something like that, that's fine too. Any questions on that? Questions on that?
I don't think so.
Okay. All right. Let's look at number 4. We're going to go through these. And I am going to have to turn some air conditioning on in this place. I got it cooled down, but it's so hot outside, and I got these lights on in here. Hold on a second. Okay, I hope that's not too loud. It doesn't seem too bad. Okay, that was number 3. Let's look at number 4. A firefighter at distance little d from a burning building directs a stream of water from a fire hose at angle theta above the horizontal as in the figure. If the initial speed of the stream is, I guess that's a little I, V initial, at what height h does the water strike the building? Use any variable or symbol stated above along with the following as necessary. G. Okay. All right. I think let's just go through this one pretty quickly. I don't think this one's too difficult. So here's the building. Here is V initial, and let's see, do we know this height? Okay. So well, all right. I guess V initial is down here at ground level. So it goes like this, all right? Okay. And we know the distance D. This height is not the height of the building, but excuse me, the point where the water strikes the building, okay? So what do we know in the X direction? We know that in the X direction, V, let me put it this way, X final minus X initial is equal to V X initial T. This is equal to D. Okay? That's that distance. X final minus X initial. You're starting over here at X initial. This is X final. All right? In the Y direction, okay, we know that Y final minus Y initial is equal to Vy initial T minus G over 2 T squared. Okay. This distance is H. All right. Now, the way they have it drawn, okay, it looks as though this stream is going up and then coming down. So it's on this part, it's on that downward part of the parabola, okay? To solve this, it's just the same way that you've done before, or we've done before. So this is D is equal to V initial, this is the angle theta, V initial cosine theta T, because Vx initial is V initial cosine theta T. Then from here we have H is equal to V initial sine theta T minus G over 2T squared. Okay? And we're looking for what? H. Okay? You can solve this for T, plug it in here, and get an expression for H. Okay? So it's asking you to get rid of T, meaning use the variables that you have in the problem, okay, to express an answer for H. So when you get rid of T by moving this around, substituting T in here, your answer will be in terms of V initial, theta, and G. And that's what you need. Are there any questions on that? Okay. Okay, number 5. A home run is hit in such a way that the baseball just clears a wall 16 meters high, located 136 meters from home plate. The ball is hit at an angle of 33 degrees to the horizontal. Okay, and air resistance is negligible. Assume that the ball is hit at a height of 1 meter above the ground. Find the initial speed. Find the time it takes to reach the wall. Find the velocity of the ball when it reaches the wall. Find the speed of the ball when it reaches the wall. Okay, so let's look at this. So in this case, here's the wall. The wall is, I don't know, they give you a height for it. Okay. I'm just going to call this Y final. Here is the starting point. And here's V initial. And this distance, this height is Y initial, which happens to be 1 meter. The distance from here to the wall, what do they give you that, right? Yeah, 136 meters. So this distance, this is from the ball to the wall. I'm going to call this delta X. That's X final minus X initial. Okay? That happens to be, for my numbers, 136 meters. Okay? So in the X direction, I mean, this is the same game. In the X direction, we know that delta X, what I call delta X, X final minus X initial, is equal to V initial cosine theta T. Did they give us the angle? I think they did. Yeah. All right, so this is theta, some angle. All right. That's about it for the X direction. For the Y direction, you have Y final minus Y initial. That's the height of the wall minus the starting height. That's equal to V initial sine theta T minus G over 2 T squared. Okay. Well, you do the same thing that I did in the previous problem. You don't know V initial, right? So what you have to do is, and I'm going to go ahead and do this, you have to solve this for T, substitute in here, and then find V initial from that. Okay? So I'm going to do that. Get rid of this. I'll start over here. All right. So I have, I'm going to call this delta Y. It'll just make the notation a little bit easier. Delta Y is equal to V initial sine theta multiplied by T. Well, T is delta X times V, T is delta X divided by V initial cosine theta T. Okay? Minus G over 2 times t squared, which is delta x divided by v initial cosine theta squared. Okay. Do we know the, wait a second. Okay, never mind. Okay. We have this. Let's see if we can solve for v initial. Okay, this term, the v initial cancels out, and you get delta y is equal to, the first term becomes tangent delta x tangent theta t. Right, because you have a sine over a cosine. T went away. We don't, what did I do? That's not right. Delta x tangent theta is that first term. Then you have minus g over 2 and a delta x squared divided by v initial squared cosine squared theta. Okay. Well, I think you can solve, I'll let you finish the algebra, but I think you can solve for v initial now because you know delta y, you know delta x, you know theta, solve for v initial. It's a little bit of algebra, but let me see. I think I had this. Yeah. Why do I have a... yeah, that's correct. Okay. Find the time it takes the ball to reach the wall. Once you find v initial from this, doing some algebra, you know theta, you know delta x, you know what delta y. Okay. Well, the time that it takes to reach the wall is pretty simple because delta x is equal to Vx initial t, which is equal to V initial, which you just found, cosine theta t. Okay. So that's part B. Part C, find the velocity components of the ball when it reaches the wall. This is part B. For part C, it's just like I did, or just like we talked about with the mug sliding off of the bar or hitting the floor, or the one I did yesterday. Vx initial equals Vx final, which equals V initial cosine theta. Okay, so that gives you the x component. Vy final is equal to Vy initial minus gt, and that is equal to V initial sine theta minus gt. Now you have the components, you have the x component and the y component of the final velocity. And they want to know the speed, I think. Find the speed of the ball. Sum of the squares, take the square root. Are there any questions on that? This was a little tricky. I mean, there's a little bit of algebra. It's not obvious, okay? You get into that changing variables, it goes, I don't know what to do. But that's why I'm here. Okay. Well, one of the reasons. Any questions on that?
So on the part to the right, are you just subbing in, so like you just rearrange the initial velocity equations to get rid of time?
Yes.
Okay.
Yeah, I had to. There was no way from either one of these equations that you could solve for the time, okay?
Okay.
Because you don't know the initial velocity. All you know are these distances. You know the difference in height in y, and the difference in or the difference in the starting and ending position in x. That's what I call delta x. That's all you really know, and the angle. So you don't know anything about the initial velocity. That's why in part A you're solving for the initial velocity. Once you have that, you're good. So.
This for problem 5, right?
Yeah. That's what I have, problem 5. Make sure when you're working these problems that you're following this plan like I'm doing. I've been doing this stuff for a long, long time, and I still have to, maybe many of you are a lot smarter than I am, but I still have to make the picture, label everything because, and write down the equations, because if I don't, I'll mess up. I mean, there's no question. So, I highly recommend that you use your good problem solving skills. Let me see, what's this next one? Number 6. All right, number 6. A boy stands at the edge of a large water well and tosses a coin into the well. The coin is thrown from a height of 2.5 meters above the water surface with a velocity of 4.45 is my number, meters per second at an angle of 60 degrees above the horizontal. As the coin strikes the water surface, it immediately slows down to exactly half the speed it had when it struck the water and maintains that speed while in the water. You getting all this? After the coin enters the water, it moves in a straight line in the direction of the velocity it had when it struck the water. If the well is 4.6 meters deep, how much time elapses in seconds between when the coin is thrown and when it strikes the bottom of the well? Okay? So, here's what I think's happening. Here's the well. There's some height h, or depth. I'll just call it h. So this is actually below ground. Okay. And up here, this stone is being thrown at some angle. Maybe it's tossed underhand. Okay. And I'll call, let me draw that larger. Let me call that theta. Okay. So it goes in, all right, and let's see, it strikes the water, the top of the water, right? Okay. Okay. So this angle, I'm not worried that we don't know anything about this angle. Let me do a close-up view of the water. Here's the water. This angle, which angle are they saying? Oh no, that's right. Okay. So this height, well, this is a, okay. This height is, I'm going to call that H. I'm going to call this D, depth. Okay. All right. So we know V initial and theta. Okay. I got it, I think. All right, now, once this coin, which is kind of weird, but once this coin impacts the water, it moves in a straight line, right? Like that, with whatever velocity it had when it reached the water. No, it's half, okay? Half the speed. Okay. This is, okay. This is 1/2 V final. This is V final. All right.
Is that drawing to your right? It'll make an impact on
Yeah.
the surface of the lake.
Yeah, this is the surface of the water. Here's the kid standing. Here's the surface of the water. And when it strikes the water, it moves in a straight line at half of the velocity that it had when it struck the water.
So is that in the problem?
Yeah?
Is half the velocity when it struck the water, or is that just
Yeah.
something we need to know?
No, it says it immediately slows down to exactly half the speed it had when it struck the water.
Okay.
Okay? All right. So let's see if we can figure out V final. Okay? I'm saying V final happens right here. Right? Because we need, if we can figure out this angle and this velocity, it's a simple matter to figure out, you know, how long it takes to get to the bottom. It's moving in a straight line. All right, so in the X direction, just like always, and I think maybe I got this. In the X direction, We don't need to know anything about, so Vx initial is equal to Vx final, which is equal to V initial cosine theta. Okay, we don't care about how far it went. Machine went dead. All right. So that's the x direction. For the y direction, okay, I want to know just, what's happening at this point of impact. So you're breaking this up into two parts. What's happening is you're solving this projectile problem from the point when it leaves the boy's hand and right before it impacts the water. Then once you have V final, then you can solve for what happens as it enters the water, okay? So in the y direction, I know that y final minus y initial, which is h, that's the difference from the top, that's the difference from where it leaves his hand to the top of the water. And I think they give us that as 2.5 meters, right? Or they gave me 2.5 meters. Okay. That is equal to V y initial T minus G over 2 T squared. Okay. And Vy initial is Vy initial is equal to V initial cosine theta. Okay. So we know H, we know Vy initial, we know G all the time. You can solve for T. You can solve for this time of the trajectory. Once you have T, I'm going to leave that up there. I'll erase this. Once we have T, we can have Vy final is equal to Vy initial minus GT. Now solving, you can get Vy final. Okay, Vy final is known. Vy initial is already known, or which is Vy. Vx final. We know Vy final. We know Vx final. We know the time. That's for the first part. All right. Now, let's look at the second part. This distance is D. That's what I'm calling it here, from the top of the water to the bottom of the well. Call this angle theta. That makes this angle theta. Okay. We need to know that. So let me call that theta final as opposed to theta that we started out with. So theta final is equal to the inverse tangent of Vy final divided by Vx final. That's going to give you a negative angle if you, Vy final, I'm assuming, well, it has to, well, it doesn't have to be, but assuming it's negative, okay? So that's going to give you a negative bit of angle. Now, Using this information, theta final, this is T in the first part. Now I'm going to call this T2. We know that V final, you have to figure that out from the sum of the squares, take the square root. V final, 1/2 V final sine theta times T is equal to D. I'll call this T2. Where did I get that from? Well, the component of the velocity in this direction, okay, sine theta final, okay, the component of the velocity in this direction is 1/2 V final sine theta final. That's this way. Times T2 is equal to D. We were given D. That's the depth of the well. In my problem is 4.6 meters. So you can solve for T2. You know theta final. You figured that out over here. You know V final. You can figure that out from here. Okay? The 1/2 came from the problem saying, well, it travels in a straight line at half of that velocity. The final answer is this T plus this T. That's the total time of the trip. Time it was in the air, strikes the water, travels at half that velocity to the bottom. I mean, look, these problems are not easy. I know that. They're not supposed to be easy. So, try these problems as soon as you can. And if you have questions, you can ask me through email or ask me tomorrow or whenever. Okay. All right, let's look at number 7. An astronaut orbiting the Earth is preparing to dock with a Westar 6 satellite. Satellite is in a circular orbit 800 kilometers above the Earth's surface, where the free fall acceleration is 8.12 meters per second squared. Take the radius of the Earth as 6,400 kilometers. Determine the speed of the satellite. Well, this one is actually pretty simple. This is just a uniform circular motion. Okay. I'll remind you of the equations for uniform circular motion. I don't think you'll have any trouble with this problem. So for an object moving in a circle, the centripetal acceleration is v squared over r. It's moving in a circle, the velocity is changing constantly. That acceleration ends up being v squared over the radius of the circle. This is that tangential velocity, okay? The period of the motion is 2 pi r over v, okay? That's often useful. You want to know, you have some information about how long it takes to go around once, that's a period, or you have some information about the radius and the velocity and you want to know the period. So what kind of information do they give here? Okay. Yeah, this is really simple. The centripetal acceleration is 8.12. That's the acceleration that's being applied to the object. So you know the radius, find the velocity. I don't think you'll have any trouble with that one. Okay, number 8. An athlete swings a ball connected to the end of a chain in a horizontal circle. The athlete is able to rotate the ball at a rate of 8.48 revs per second when the length of the chain is 0.600 meters. When he increases the length to 0.900 meters, he is able to rotate the ball only 6.6 revs per second. Which rate of rotation gives the greater speed for the ball? Okay, let's talk about this for a second and figure out how to make sense of this revs per second. Okay, so frequency is the inverse of the period. The frequency is equal to 1 over the period. The frequency is how many times does it go around in a second? Or how many times does it go around per second or per hour? Okay, so when you're given something in revs per second, okay, that means revolutions per second. That's how many times it goes around in 1 second. Then the frequency is equal to 1 over the period, and likewise the period is equal to 1 over the frequency. Periods in seconds typically. Okay, so when you're calculating this, it gives you the revs per second, right? And then in part, you can figure out part A. That's simple. What is the centripetal acceleration of the ball at 8.48 revs per second? So you can use this, solve for T, solve for V. You're not going to have any trouble with that. It's real simple. Okay? All right, we have a few minutes. I know I skipped 1, 2, and 1 and 2, or maybe 1, 2, and 3. No, I skipped 1 and 2. Let's take a minute to look at 1 and 2, although those are sort of just exercises dealing with these vectors and so forth. Let's take a look at 1 and 2. Okay, number 1, suppose the position vector for a particle is given as a function of time by r of t is equal to x of t I hat plus y of t j hat, with x of t equal to at plus b and y of t equal to ct squared plus d. Okay, that's a lot of information. So r, what they're saying is the position is some, let me write it like this, some function of time. It's x of t I hat plus y of t j hat. Okay, where x of t is equal to, what is it, a t plus b. So x of t is linear, at plus b. A and b are constants, and y of t is equal to ct squared plus d. So y is quadratic. Okay. That much we know. So they give you values for A, B, C, and D. calculate the average velocity during the time interval from 2.2 seconds to 3.9 seconds. Okay, some delta t. All right. So what you have to do, so you have delta, let me say, delta t. They give you some t final. Let's look at it this way. T initial. So the average velocity, V average, is equal to delta R divided by delta T. How are you going to find delta R? Well, delta R is R final minus R initial, and you divide by delta T, which is T final minus T initial. To find R final, you take these values or these equations, you plug in T final, and you get a value for Y and a value for X. To find R initial, you plug in T initial into this, and you find values for R based on that time. That's R initial. Take the difference, looking at the difference in the X components and the difference in the Y components, and calculate delta R. So that's part A. Part B, determine the velocity at t equals 2.20 seconds. All right. Well, the velocity at t equals 2.20 seconds. Now that's an instantaneous velocity. Remember that v is equal to dr dt. The instantaneous. They're not asking you for the average velocity. They're asking you for the instantaneous velocity at some instant of time. So this is equal to dx dt I hat plus dy dt j hat. Okay? dx dt is equal to A. dy dt is equal to 2ct. Okay. Plug those values in, and some of the squares take the square root because you're finding the components of the velocity, and that'll give you the magnitude of the velocity at t equals 2.20 seconds. Wait a second. Well, yeah, okay. Determine the speed. So I guess for the velocity, how are you supposed to enter that? Let me see. Oh, they've got, okay. This little thing over here that has vectors, so you can put in I hat and j hat. Okay. No worries with that. Any questions on that? Any questions on anything else?
I don't think so.
Okay. All right, so for tonight, I would say, work on these homework problems. Well, I'm a little bit worried about having this test on Friday. Today's Wednesday. I don't know. Yeah, let's just keep the test. I'll think about it, and I'll send you an email this afternoon sometime for the test. And for those of you that are in the lab, so I'll send you a data set for the stuff in the lab and for the report. And that won't be due till maybe next Thursday, so a week from tomorrow, something like that. So you don't have to worry about that too much right now. Okay. Any other questions on anything? Okay, I really appreciate you guys showing up this morning. So if you need me, let me know.